Hello everyone, I'm Nakul, a research engineer at Alpen Labs building Glock. Today I'm going to talk about how gobbled locks or glocks are used to obtain conditional disclosure of a secret on Bitcoin. This gets into some of the very interesting cryptography that Glock uses to authenticate off-chain computation. In the previous video, Mukesh spoke about a magical check function that looks at an encoded input and it reveals a secret if and only if that input fails some authenticated check. In the previous video, we treated this magical check as a black box and discussed how it might be useful for computing on Bitcoin. The goal of this video is to open that black box and see how one might implement this magical check using gobbled locks. Recall that we use a specific way of encoding inputs that works well with Bitcoin. In particular, we assign two keys for each bit of our input, red for zero or false, green for one or true, and the gobbler commits to his input bits by sending one of two keys for every bit. For example, the gobbler could commit to his input of 0 1 1 0 1 0 1 0 by sending the keys in this table. We denote the final secret, the one that is actually conditionally disclosed, as the golden key. And this is only revealed if the input fails this authenticated check. We'll start off with a simple checking algorithm that takes as input two bits and checks whether both are true or one. We can think of a Glock as a lock with multiple keyholes that possibly holds another key inside it. The gobbler sends four Glocks out here. Each of these Glocks can be opened by a different input key combination. So the evaluator will only be able to unlock one of them based on the input keys that he receives. In this case, the gobbler would lock the golden key within the first three Glocks and not put anything inside the fourth Glock. Any combination of keys other than green, green, or 1, 1 can be used by the evaluator to open one of the first three Glocks and obtain the golden key. In other words, the evaluator obtains the secret if and only if the gobbler's input keys do not pass the checking algorithm. This is exactly what we wanted to achieve. However, recall that in practice, this checking function can be as complex as verifying a zero-knowledge proof, which requires many more input bits. The issue with the above solution is that it does not scale very well for long inputs. So let's consider another very simple check that now instead takes an input of length 4 or 4 input bits and checks that they are all true or 1. Using the same approach as above, the gobbler can send a Glock for every input key combination, where the first 15 such Glocks will hold the golden key, and the last one will hold nothing. Again, this way, when the gobbler sends over these Glocks, the evaluator can disclose the secret if the gobbler's input does not pass the check, which is if the evaluator receives anything other than green, 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 green. So notice that this solution, it requires one lock to be sent over per key combination, and that's too many Glocks. For example, consider a function that takes in 30 inputs, which is quite realistic. That would equal to 2 raised to 30 Glocks, which is more than a billion Glocks to be sent over. To get around this issue, we break the checking computation into smaller chunks, and instead we send Glocks for each chunk. Notice that the previous condition, the previous checking function that we had, which is that all four inputs must be true, that's equivalent to checking that the first two inputs are true and the last two inputs are true. Therefore, we can evaluate this checking algorithm in chunks as follows. We'll feed the outputs of the first two chunks as an input to the third chunk, which then computes the final output. In this way described, we would feed the first two input bits in the first chunk, the last two input bits in the second chunk, take the outputs of that and feed it into the last chunk. The final output would be true if and only if its inputs are true, and its inputs are true if and only if all four inputs are true. More generally, a circuit is a decomposition of a function into many such small steps called gates. This is actually where the term gobbled circuit comes from. Looking at how we would evaluate such a circuit, For example, on the input 1011, we would evaluate this per chunk. So on the first gate, we evaluate 1 and 0, and that gives us a 0 because each chunk needs to only passes if both of its inputs are true. So a failing input here would propagate the red wire up, and a red and green would finally propagate a red wire in the output. So this input causes the output to be 0 or false, as opposed to the passing input with all ones, that leads to a final true or one output wire. The connections between components are called wires, and wires take the output of one step and feed it as input to another step. We now show how to gobble a circuit. Our goal remains the same, but we want to try and use fewer Glocks to achieve the same effect. This time, the gobbler picks red and green keys, not only for the input keys, which were used as commitments, but for all wires in the circuit. This corresponds to the fact that now we encode not just the inputs to the function, but all intermediate values in the computation as well. Our goal is then for Glocks to propagate these keys or encoded values according to the logic of the gate. The key insight is that Glocks can now hold keys that are used to unlock other Glocks. In particular, the gobbler creates such clocks per gate of the circuit and sends them to the evaluator. So, looking at the one on the top left here, the first three clocks actually hold the red key for the output wire, and the last one holds the green key for the output wire. Now, what the evaluator can do is use input keys to obtain an output key per gate, use that as an input key for the next gate, and eventually reveal the golden key. For example, assume that the evaluator has received a green, red, green, green key as inputs. He can use the green and the red keys for the first two input bits and use that to obtain the red key for the next wire. Similarly, he can obtain a green key from the second chunk. Using this, he can use the red key and the green key to finally obtain the golden key for the output. Notice that if the clocks are correctly formed, an evaluator can obtain the golden key if and only if the gobbler's input keys correspond to a failing input. Does this really make a difference though? Consider the 30 input checking function, where we accept if all inputs are true. If we created one Glock per input combination, that's more than a billion total Glocks. Instead, if we decompose the check into about 30 AND gates and we created 4 Glocks per AND gate as we did before, that leads to a total of only 120 Glocks. And in practice, our checking function has more than 1,000 inputs, so we must decompose it into gates before creating Glocks. In a supplementary video, we will dig a little deeper into how the Glocks and keys themselves are instantiated, usually as encryptions of large random numbers. We'll also look at some optimizations that further reduce the number of Glocks that need to be sent over and stored, as this is the key bottleneck in practice. Thanks for watching and stay tuned for more Glock explainers.